Welcome to a lesson with Dr. Powell. Let's take a look at how we can find the equation of a line in 3 dimensions. Now, a line is very one-dimensional. In 2 dimensions, the equation of a line might look something like this. Y is equal to 2x plus 3. Notice that it's a function with an output and the input. And the input, there's only one variable coming into it. And the result of the graph, the solution, is going to depend upon that one input value because it's a function, depends on the input. And so since it's completely dependent upon something that's one-dimensional, meaning one thing coming in freely here. And we can see that in the graph. The graph is a straight line, and that straight line is very one-dimensional. Okay. It's very analogous what we do here in 3 dimensions. So what we're going to do now is notice, so that's like slope, and x is like here, we have x here, and then we have a b for maybe intercept. So we're going to replace this b with a starting point. That's kind of what it is. It represents like a y-intercept. Here we're just kind of making a starting point. This m is going to represent a slope, but we're going to represent it as a vector, kind of like a slope vector, say. And the starting point, let's make that a vector too, because every point in 3 space can actually be thought of as a vector from the origin. So we're going to represent all the points in the line via some kind of vector deal. So what we're going to do is we're going to have a starting vector, and what we're going to do to it is we're going to add another vector to it. We're going to add scalar multiples of that vector. In other words, we're going to rescale it, multiply it by a number. This is just a number that you're going to rescale with. And for our purposes, let's not use x, but since we're already dealing with x, y, z as coordinates, let's have something external, maybe like t value. So the input's going to be very one-dimensional, but let's not use x this time. Let's just use a t. That's going to be a parameter. So we're going to have some kind of a slope vector. And because it's a vector, let's not use m, but let's use v. And starting, let's make this a p sub 0, p naught. Okay. And this is like a vector function. Maybe we could use vector notation here. And then maybe this is a vector function like this with the input of t. Okay, where t is a parameter value. Okay, let's kind of think of what's happening. We have a point, p naught. We have the origin right here. All right. Oh, so then we have a vector coming to there. And so that's what p naught's going to represent. Then we have a vector v coming from this. Maybe it's like a slope vector or something like that. Okay, so it's representing, well, just representing anything. It could be any vector at all. But it's going to determine a line, because what we're going to do is we're going to add on to p naught this vector. You notice how I drew this vector where the tail of it was right at the tip of p naught? That's because, look, we're adding it. All right, and if we add it, we get here. Now, what if we added like 1/2 of v? 1/2 of v would be right here. And if we added it, we would get right here. Notice that these 2 points are on a line, the line that v makes going this direction. If I were to add 3 times, or well, let's just do 2 times v, we'd get to here. And if we add, we get to this point. And notice that all those points are on the same line. If I did a negative version of v over here, I'd be over here adding. Notice that any multiple of v that I add to p naught gets me on this line where I end. The ending tip is on this line. So really, this vector addition puts me on a line. And that line is in the direction of v. So v is kind of like the direction I'm going to be traveling away from p naught. And then t just kind of rescales that direction, again, this way or that way, back and forth, and I get a line. So that's pretty much the equation of a line. So we need 2 things. We need to have the equation of a line. We need a vector, and we need a point. Just like we could think of a slope and a point, here we'll say a vector and a point. Because honestly, this vector we'll see in a minute is a lot like slope. Okay, so let's look at a specific example. What if we have, for instance, a vector v of 1 to -3. And suppose we have a point to start off with as 2, 0, 1. Okay, so we're going to start from this point, and we're going to be adding on onto this with this vector. So the equation of the line is going to simply be, well, we essentially have it. It's just t times this vector. So it's t times v plus p naught, really. We could think t times this vector would be, we can multiply t in here to everything. Then we just add. So we end up getting, and we can do it component-wise. So we end up getting t plus 2, 2t, and -3t plus 1. So this first coordinate is like, is an x value of this line that's going along. And we could think of it, and that x value, that x coordinate is actually a function of t. You can see that. So we could even write x of t as that. Similarly, y of t is this, z of t is this. This would be the parametric form of this line. Now, we could go a step further and come up with what's called the symmetric form of the line if we just solve for t in each one of these. So solving for t here, just thinking of this as x, t plus 2 is equal to x. Subtract the 2 over, you see what t is equal to. T is equal to x minus 2. What else is it equal to? Over here, let's see, t over here is equal to y over 2. What else is it equal to? Solve for it. Let's see, z minus 1 over -3. Okay, so we could write something like this down. This would be like the symmetric form of the equation of the line. But notice all these are equivalent. They're all the same thing, just written in different ways. So parametric with the equal here of those. This is the symmetric. And if we just kind of leave this alone, just like here in vector notation, that's the vector equation form of the line. So, but really they're all equivalent. They're really all the same thing. So now notice, what is x prime of t if we take the derivative with respect to t? It's 1, right? And y prime of t is 2, and z prime of t is -3. Notice if we put those together, 1, 2, -3, what do we got? We got our original vector we started with, 1, 2, -3. Literally, quite literally, the slope, how fast the x coordinate is changing with respect to t per every unit, 1 unit of t, how much it goes up, how much this one goes up every unit of t, how much this one goes up, which is actually negative, so it's going down per unit of t forward. So really is mx plus b, and that's kind of how to work through that. Thanks for watching.